So before we start looking at example 4 in the notes booklet, let's figure out why it's important to know that first quadrant of reference angles. So if I want to fill in my circle template in degrees, remember there's 360 degrees in one revolution of the circle, and this would be 30 degrees. And then that's 1 times 30. This is 2 times 30, which is 60. 3 times 30 is 90. 4 times 30 is 120. Then 5 times 30 is 150. 6 times 30 is 180. 7 times 30 is 210. 8 times 30 is 240. 9 times 30 is 270. 10 times 30 is 300. 11 times 30 is 330. And then 12 times 30 is 360. So that brings us one rotation around the circle. Slide that back up in the right spot. Okay, now if we want to do the missing angles, the 4 that are missing, those are the 45s. And you can see that that's halfway between 30 and 60 would be 45 degrees, which is like taking 30 plus 15. Right, to get to 45. 45 plus 15 gets you to 60. So 120 plus 15 is 135. 210 plus 15 is 225. And 300 plus 15 is 315. And that's an easy way to fill in your degrees as you count around the circle. Okay, now for radians, there are 2 pi radians in the whole circle. Half of that is pi. Half of that is pi over 2. And half of that is pi over 4. So counting in increments of pi over 4, this is 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, which reduces to 3 pi over 2, 7 pi over 4, and then 8 pi over 4, which reduces to 2 pi. And then divide my circle into 6 pieces, each 60 degrees. That would be pi over 3. And notice the pattern here, how this is pi over 2, pi over 3, pi over 4, right? 2, 3, 4. That pattern, though, is going to break here at 30 degrees because 30 degrees is pi over 6. But the first 3 do follow that pattern where the denominators are 2, 3, 4, and then that'll help you remember your first quadrant in radians. So if this 60 degrees is 1 pi over 3, then 2 times 60 degrees is 2 pi over 3. And 3 times 60 degrees is 3 pi over 3. That would make 240, 4 pi over 3. And then 300 degrees would be 5 pi over 3, since that's 5 times 60. And then 6 pi over 3 gets us back to 2 pi. That leaves just our pi over 6 angles here that need to be filled in. So at 30 degrees, we have 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. This is 5 pi over 6. Remember, half the circle is 6 pi over 6, so 1 before would be 5. 1 after would be 7. So this is 7 pi over 6. Then 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6. And that's all of our radian measures going around the circle. Okay, then we want the coordinates, and this first quadrant you can fill in remembering the following pattern. So if you start up here at the top, this is 0, 1, 2, 3, 1. Now we're going to do the same thing in reverse. 0, 1, 2, 3, 1. Okay, then each of these in the middle is going to get divided by 2. So we divide all of these by 2. And then we square root the numerators. And the square root of 1 is 1, so I don't have to write the square root there. Then square root both numerators. Square root of 1 is 1, and then square root of 3. And that gets me my coordinates for these special angles. So once I know that first quadrant of special angles coordinates, all I have to do is reflect them into the other quadrants, remembering that in quadrant 2, the x is negative and the y is positive. In quadrant 3, both x and y are negative. And in quadrant 4, x is positive, y is negative. So I'm using these first quadrant angles as references to get the other quadrant's coordinates. So for example, 5 pi over 6, when I reflect that into the second quadrant, the magnitude of the ordered pair stays the same, but the direction is now different for the x. So the x is a negative square root of 3 over 2. The y is positive 1/2. Similarly, when I take my pi over 4 and reflect it into the second quadrant, at 3 pi over 4, I'm using pi over 4 as the reference. So I have a negative square root of 2 over 2 for my x coordinate, positive square root of 2 over 2 for my y coordinate. Then at pi over 3, 1/2 root 3 over 2 in the second quadrant becomes negative 1/2 root 3 over 2 as the coordinate for 2 pi over 3. Okay, then when I reflect my 1, 0 ordered pair over the y-axis, I'm at negative 1, 0, because my x becomes negative. Similarly, when I reflect my 0, 1 over the x-axis, right now my y value becomes negative. So as I take each of these points and I reflect them into the third quadrant, both the x and the y are negative now. So 7 pi over 6, it's referencing pi over 6, so they have the same magnitude, but both the x and the y coordinates are going to be negative because we're in quadrant 3. 5 pi over 4 is referencing pi over 4, so they have the same magnitude, but the signs are both negative. And then for 4 pi over 3, we're referencing pi over 3, So negative 1/2 and negative root 3 over 2. Then in quadrant 4, the x is positive, the y is negative. So 11 pi over 6 is referencing pi over 6. So they both have a positive square root of 3 over 2 for their x. But the reference angle, pi over 6, when I reflect it into the fourth quadrant, makes the y negative. So y will be negative 1/2. 7 pi over 4 has a pi over 4 reference. The x stays positive. The y is negative. And 5 pi over 3 has a pi over 3 reference. The x stays positive, and the y is negative. So now that we see why the first quadrant is called the reference angles, we can use that idea of just the first quadrant to help us determine the coordinates at other values on the unit circle without having to recreate the entire circle. So 11 pi over 6, that's reduced and it has a denominator of 6. So pi over 6 is my reference. That means it's going to have a coordinate that has a magnitude of root 3 over 2 comma 1/2. We just need to know what quadrant it's in so we know what signs to use. So 11 pi over 6, if the whole circle is 12 pi over 6, that's 1 back, 1 pi over 6 in the clockwise direction. That puts us in quadrant 4. So since this is a quadrant 4 angle, the x is positive, the y is negative. So we use our pi over 6 reference, root 3 over 2 comma 1/2, but in quadrant 4, the y is negative. And that would be the coordinate of 11 pi over 6. In problem B, 5 pi over 4, this has a denominator of 4, which makes this a pi over 4 reference angle. And 5 pi over 4, if I think about where that is on the circle, this is 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. So 5 pi over 4 is going to be in quadrant 3. So I use a negative x and a negative y in quadrant 3, along with my reference of pi over 4. Gives me a coordinate of negative root 2 over 2, comma negative root 2 over 2. Okay, then in C, negative 4 pi over 3. So again, on my circle, if it's a negative angle, I'm going in the clockwise direction. This would be negative 1 pi over 3, negative 2 pi over 3, negative 3 pi over 3. You should be negative. And then negative 4 pi over 3, which would be in quadrant 2. So I'm using a pi over 3 reference, but in quadrant 2, x is negative and y is positive. So a negative 1/2 and a positive root 3 over 2. Then problem D, 11 pi over 3. That I need to find a positive coterminal angle that's closer to 0. So I don't have to count around the circle more than one lap. So if I double my denominator, that's a 6. So I'd have 6 pi over 3. 2 laps around would be 12 pi over 3, which 11 pi over 3 plus 12, or sorry, minus 12 pi over 3, which is 2 laps around. That would be negative pi over 3. And I know then that that is in my fourth quadrant. So I'm using a pi over 3 reference, which has an x-coordinate of 1/2. That's positive in quadrant 4, but y is negative, so negative root 3 over 2 is my y value. So that brings us to the secret question for this lesson, asking what is the coordinate at negative 17 pi over 6, at 13 pi over 4, negative 600 degrees, and 11 pi over 2. So you want to try to reason those out without looking at your completed unit circle if possible, using what you know about reference angles and coterminal angles in radians and degrees. Don't forget to show your work or explain your reasoning for each of these problems and include it as the last page when you upload your notes to Schoology.